In this section, we'll talk about expected value. Okay, so the mean or average of a set of observations is just kind of their ordinary average. That's what we're used to. But we can also look at the mean of a random variable x. So the mean of a random variable we still think of as an average of the possible values of x, but we need to take into account that not all of our values will be equally likely. So let's suppose we repeat an experiment an indefinitely large number of times, so infinitely many times. If we were to record the values of the random variable x, we would obtain a very large population of all the possible observed values of x. So for example, if we were to roll a six-sided die many times, let's say like 1 billion times, the results could look like this. Maybe it'd be a 2, 1, 4, 3, 5, etc. So basically, these are all the results when I roll the die, and we're doing this infinitely many times, or 1 billion times, or 1 trillion times. So this would give us a population of possible x values, or in this case, a population of x values. We would like to know the mean, or the average, of this population of all the possible observed values. We would call this the expected value of x. So expected value of x, or we could do this little mu for expected value, or we used this before for mean. So it's the mean, and we put an x on it to tell us it's the mean of a random variable x. So the expected value is our average result if you do something many, many times. So it's the average if you do something many, many times. So to calculate it, if we have a discrete random variable, suppose x is a discrete random variable whose distribution, so for each x value we have a probability, so x1, p1, x2, p2. To find the mean, or expected value of x, or the average of all the possible values, we multiply each possible value by its probability, then we add all of these products. So we'll do x1 times its probability plus x2 times its probability. Notice this sigma sign, this is the sign for a sum in mathematics, so it says just add up each x times its probability. And I have here, this is expected value of x. Sometimes we'll just use mu instead to tell us it's the expected value. Let's look at an example. So we have the chance to play a game at a carnival. We have this wheel. We can spin the wheel and gain or lose the money that the spinner lands on. And the ticket price is already calculated into your winnings or losings. So your possibilities, the amount you can gain is -100, so you must be paying 100 to play. And there's a 60% chance you get that. There's a 30% chance that you get 100, 9% chance you get 500, and 1% chance that you get 1,000. So first, gut feeling, do you think you should play this game? Yes or no? If lots of people play the game, do you think the carnival is going to win or lose money? So if you are going to spin the wheel once, do you think you're likely to win or lose money? Okay, so this is just what you think. Let's actually try this. So in Excel, I simulated this spinner. So every time I push the button, it will spin it. So right now I just pushed it and it says we lost $100. So it looks like every time I keep pushing it, I'm losing $100. And it looks like, oh, there I won $100, but I lost. Keep losing, I won, lost, 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 lost. Oh, this time though I won $500. Lost, won, lost. So you can see every time I'm getting different results. And it might be hard just kind of looking at this to get a sense of, okay, if I'm doing this many times, am I winning or losing more? So this is why we like our formula. So we can go back again and actually find our expected value. So let's let x be the amount we gain when we spin the wheel. The possible values were -100, 100, 500, and 1,000. Let's assign it the probabilities. So this is just the percentage of area. So we'd have 0.6, 0.3, 0.09, and 0.01. Now let's find the expected value. So the expected value of x is just as add up each x value times each probability. So my first x value is -100. Make sure you use that negative. So -100 times 0.6. Plus my next x value is 100 and its probability is 0.3. My next one is 500. Its probability is 0.09. And finally 1,000 times 0.01, which equals 25. So my expected value is 25. So this means even though on one spin you either lose 100 or gain 100, 500, or 1,000, in the long run, this means if you played this game many times, you would get an average of $25 per game. So again, this is if you play many, many times, you'll get an average of $25 per game. This means the casino is losing an average of $25 per game. So this is a game that would never last in Vegas because they don't want you to be winning every time. They want you to lose on average so that they can make money. Here's another simple wager. Let's say you pick a 3-digit number, 0 to 99. The state chooses a 3-digit winning number at random and pays you $500 if your number is chosen. But you had to pay $1 to win. So let's let x be our net winnings and find the expected value of x. So let's start by writing down our possible x values and our probability. So the amount that we win, if we win, we get $500, but we had to pay $1 first. So this would be 500 minus 1 equals $4.99. And the amount you lose, we get paid 0, we had to pay $1, so this would be -1. Now the probability, you could only pick one number, or there's only one right number out of 1,000 possibilities, so 1 out of 1,000. And then to lose would be 999 out of 1,000. So to find the expected value of x, it would just be, again, the sum of each x value times each probability. So my first x value is 499 times the probability of 1 over 1,000 plus -1 times 999 out of 1,000, which gives me -0.5. So what does this mean? This means if you played many, many times, you will lose 50 cents per game on average, which means that the state is going to be making 50 cents a game on average, so they will make quite a bit of money if people play.